let me introduce our today's speaker. Roberto Martin-Martin is an assistant professor of computer science at the University of Texas at Austin and director of Robotic Interactive Intelligence Lab. His research integrates robotics, computer vision, and machine learning. He is interested on integrating physical interaction as synergistic component of robot perception, planning, and manipulation skills. Previously, he worked as a postdoctoral scholar at the Stanford Vision and Learning Lab with Professor Silvio Savarese and Fei-Fei, where he coordinated research projects in two groups, the People, AI and Robots pair team, studying visuo-motor learning skills for manipulations and planning, and the iGibson behavior team, examining problems in long-horizon mobile manipulation and human cognition. He also led the Jackrabbot team, where he studied mobile manipulation in human-populated environments. He received his doctoral and master's degree from Berlin University TUB and his BSc degree from Universidad Politécnica de Madrid. Roberto's work has been awarded the RSS Best System Paper Award and nominee for ICRA Best Robot System Paper Award, IROS Best Paper Award, Best Student Paper Award, and Best Cognitive Science Paper Award. He has been selected RSS Pioneer, and he is the chair of IEEE RAS Technical Committee in Mobile Manipulation. So let us introduce our speaker to start the talk today.
All right. Thank you for the introduction. Let me share my screen. Let's see. I usually use Zoom, so it's going to be an experience to use Google for this, but I think that should work. Can you see my screen?
Yes, we can see it.
Okay. All right. Yeah. Thank you so much for the presentation. So today, in the title of my talk and the abstract that I sent around, what I want to do is to take one step back and talk about something that we usually don't think so much in robotics or in embodied AI, which is what do we actually want robots to do for us, and then how can we get there? So I will tell you about the efforts in my lab, trying to bridge the gap between where we want to be and where we are right now in robotics. And yeah, basically that's going to be the talk today. Let's get started. So to give you kind of like a historical overview, since we have registers or records of human stories, we hear about the desire of creating some form of machines or artificial intelligence that could help us with tasks. And we have been asking ourselves, what can we do with these machines? What can we do with these kind of like robots, even before they were called robots? One of the first ones that we know about is the robot or machine called Talos, which was a bronze giant created by the god Hephaestus in Greek mythology. And Hephaestus gave Talos to the king Midas and asked him, what do you want to do with it? And King Midas said, okay, what I want is to protect the island of Crete. So that was what he decided to do. And this robot was kind of like impeding that Jason and the Argonauts could reach the island. So a very clever woman called Medea convinced the robot to remove a screw from its uncle, and then all its vital liquid flew away, and the robot kind of like deactivated itself. That's one of the stories. Another set of stories of AI before they were called robots comes from the golem stories from Jewish tradition. And here what was going on was there were some masters that were creating these golems from raw materials, and usually what these masters wanted, what these humans wanted from the golems, were some kind of protection against aggressors. An interesting thing about these stories from golems is that they end up very often with the golem running amok and being a threat for the master itself. So what do I get from these stories? Well, the first thing is that in ancient times, They were very dangerous times. So what humans wanted from robots or from artificial intelligent agents was to have protection. The second thing that I get is that even centuries ago, women were very good roboticists that could deactivate giant bronze robots. And also that the robot apocalypse is not such a new story. It is actually a pretty old story, centuries old. But let's go more into kind of like modern times. What is what we want robots to do for us? I think in modern times, we have improved in security and safety in our lives. So we're more interested on getting rid of these tedious tasks that we don't want to do, especially in our homes, like cleaning, doing laundry, going somewhere to get groceries for us. These kind of tasks are kind of like very interesting for everyone to get some form of robot to do. But there is not only this desire, there are also some deeper and pressing economical forces pushing to have some form of AI helpers that can do these household chores, these everyday chores for us. For example, just in the US, in the next years, the age population is going to increase, while at the same time, the ratio of caregivers available for this age population is going to decrease. So this is only in the US, Europe, Japan, the situation is even more severe. So all the eyes are looking at robotics, and there's a lot of pressure from these economical forces to have robots that can take some of the chores and some of the tasks in household environments and do them for humans. But actually, what tasks do we want robots to do for us? What do we really want robots to take from us, from our everyday list of tasks? So I'm gonna propose you a game. I'm gonna give you 5 seconds to think of if you would have a robot that could do household work for you, what would you like this robot to do? So I give you 5 seconds. Just think about it, and yeah, then we can continue. So you maybe want this robot to clean the kitchen floor for you, or to shovel snow for you when there is some kind of like storm. What about folding laundry? That's probably something that everyone wants robot to do for them. And what about cooking breakfast? That's a difficult one because some people actually enjoy that. And shopping shoes for you? Do you want a robot to do that for you, or do you want to do it yourself? And finally, now is a very good time for asking this. Do you want a robot to open the Christmas presents for you, or do you want to do it yourself? This is a household chore. All right. So what this exercise tries to illustrate is that we need to align what people want robots to do with what researchers in robotics try to get robots to do. Because if we can align both goals, we can create robots that do what is really needed. And that has been the motivation we followed to create Behavior 1K, Behavior 1000, which is a new benchmark in simulation for robotics with 1,000 household activities. As I will explain in a minute, these activities align to human preferences, making Behavior 1K the first human-aligned benchmark. Apart from being aligned to human preferences, we bring new levels of realism, diversity, and complexity in this benchmark, with the idea to reduce the sim-to-real gap and make solutions to transfer more easily, like we will see at the end of this part. So our goal is to facilitate research in robotics and embodied AI in a direction that actually is significant for people. So how do we get that? How do we figure out what people want robots to do for them? So what we did was to carry out a very large survey. First, we collected 2,000 candidate activities, and to get these candidate activities, we looked into something called TUS surveys, time use surveys, which are surveys carried out by bureaus of labor statistics here in the US and in other countries. basically asking people, what did you do yesterday? Where did you spend your time? And then they collect all this information about what people do in their everyday lives, and they report these statistics of what people invest their time on. So we took those activities, because it's mainly a lot of activities that have to do with household chores. And we also compensated with or included additional activities coming from WikiHow. WikiHow is this large repository of instructions, explanations on how to do activities. And many of these explanations are actually about household activities, how to perform household chores, like how to fix a broken lamp, or how to cook certain recipe. All of these can be found in WikiHow. So we collected all these possible activities, 2000, and then we went into Amazon Mechanical Turk, and we asked people, how much would you benefit if a robot would do this for you? They can basically rank it in a 10-point Likert scale, and we tried to get a population of participants in our survey that was well distributed in terms of gender, level of income, and age, so that we get as much as possible unbiased responses of what people want robots to do for them. By the way, I didn't say it at the beginning, but if you have questions, feel free to interrupt. So I'm fine with that. If there is kind of like a question that pops up in the moment, it's better to kind of like answer it. Yeah, I think there was a question or something. All right.
Yeah, I have a question. Yeah.
Yeah, go ahead.
You just proposed to ask if we have.
Yeah.
Yes. Don't you think that currently, like, the major AI activities are targeted towards not the like low-level things like household activities, etc., but towards like, I don't know, painting, I don't know, drawing pictures, writing music, writing poems, like, as we can see, like with current like DALL-E, ChatGPT, etc., but not towards the low-level activities. What do you think here?
Yeah. So this, I would say, is more on the side of what AI in general can do for us, and also it's a bit unclear if that is actually what people would put the first. I mean, if you could ask, what do you want AI to do for you? I don't know if I would put the top of it to draw. I don't know, to make a very realistic picture of a teddy bear in Times Square. I think that would be very low in my list, but I think it's what we can do as researchers. But this is very focused to embodied AI, to interact with machines. Here's not just about AI in general. Here's about if you would have an agent that could change your physical world in some sense, what would you like this agent to do for you? And that is kind of like the different aspect. But I completely agree. Right now, is going in a very different direction in AI in general, with these large language models, foundation models in images, in video, etc.
But do you think that for embodied AI we have like the opposite direction? For example, most of the embodied AI research is targeted towards like household activities or autonomous driving or etc., which is very like, which has very high utilization ratio or something.
Yeah, that's a very good question, and that is maybe something we should do in general also for AI. Are we investing on where people really want AI to be active or not? So we are partnering in this part of the kind of like the study of what people want robots and AI in general to do with us, with a professor also from Stanford now. He was at MIT before, Eric Brynjolfsson, I think is the pronunciation of his name. He studies how much weight had different activities in GDP. And one of the things that he asks people is, how much would you pay someone to do this for you, and how much would you ask someone to pay you to do this for someone else? So this is his unbiased way to try to give value to different products in society, because he has this basically this hypothesis that some things are not measured correctly in GDP. For example, household activities are not part of what GDP measures, because GDP was kind of like created in the 50s, 60s, and household activities was something that was not productive at the time, not considered to be productive, but it's a big part of what people work on and this productivity in some sense. So he has this other way. So what I'm trying to come to is, we should ask something similar for AI. What do you want AI agents, not embodied agents, AI agents in general to do for you? Is creativity, or is actually something that releases your time to be creative yourself? Yeah, that's a very good question. I don't know. It's very different trend what we see in not embodied AI and embodied AI.
Thank you. Thank you. Please go on.
All right. So, okay. So this is the way we studied the problem. So what did we obtain? On the left, you see the distribution of preferences over the 2,000 tasks. And on the right, you see some of the top activities and the bottom activities. So it's not a huge surprise, but what people want, at the top of what people want robots to do for them are things like cleaning after a wild party, or cleaning grease, or scrub the bathroom floor. And at the bottom are things that are actually also considered household activities, but are more recreational or more personal, like buying a ring, mixing baby cereal, or even playing squash. It's considered a household activity for this time use surveys from the labor statistics. So another thing that we observe is that the distribution shows a large statistical dispersion, which means that humans want robots to perform a wide range of activities for them. And we can actually cluster these activities based on language, and we observe very clear superclasses of basically families of tasks that people want robots to do for them, which is basically cooking, cleaning, repairing things in their home, doing yard work and garden work, and considerable also cluster, which is buying and bringing groceries from stores, which I think could be of interest to you. All right, so what we did then is we went ahead and we picked the 1,000 tasks, and we created a simulated version of them for robots to try to solve them. So for example, cleaning after a wild party, cleaning a shower, setting up a dinner table, cooking dinner, or filling a bucket in a small sink. So all of this is in simulation. And so why in simulation? Why not in real world? Well, in the last years, there has been a lot of progress in embodied AI thanks to simulation environments because of several reasons, but the most important ones can be summarized in 3 reasons. The first one is that simulators enable fast, diverse training to create policies that can transfer from simulation to real world. That was very well illustrated with the project Dexterity from OpenAI, where they train a simulated hand, collecting years of experience in just a few weeks, and then they could transfer the policy into a real setup in a real hand. That is what you see here on the top right. So also, when it comes to household activities, we want diversity. We want agents that can train in one environment, in several environments, in simulation very quickly. If we need to do it with a real robot, we will have to bring the real robot to several houses. That's already logistically very time-consuming. In simulation, you can just start the simulator with a different house model, and that's it. So it's very practical. But there are more reasons. The second one is that it's safe for robots and the environment. So robots are super expensive. The environment is delicate. So we don't want to put it in risk. Simulation is a perfect playground. And the third reason, which is also important, especially from the lab that I was before at Stanford, is to create fair and reproducible benchmarks to evaluate the different solutions in fair and equal conditions. That was what ImageNet did for computer vision, but in robotics, there's not an equivalent thing. So we wanted to bring more proper benchmarking for embodied AI. All right, but in order to get to these benefits, for example, the first one, to have a diverse and fast way of training policies, we need diversity in our simulation. So that's why we bring 50 different high-quality, full interactive scenes for these agents to train on. And this includes houses, hotels, grocery stores, restaurants, schools, etc. So here you see one of the models that we have in Behavior 1K in order for robots to perform tasks, cleaning tasks, and rearranging tasks. This is an office scene. We also include over 1,200 object categories and over 5,000 object models that are annotated with semantic properties like their friction parameters, their weight, if they can be cooked, if they can be frozen, etc. And all these annotations are coming from internet sources to be as realistic as possible. All the objects are fully interactive. If they have articulation, the agents can kind of like open doors or drawers or move the scissors, etc. So comparing to existing benchmarks, there are a few benchmarks out there. We have bring a new level of diversity in terms of the number of activities, the scenes, the objects, and other dimensions that allow to have diversity in training that bring more generalization in the solution. In fact, when we started this project, we wanted to use one of the existing simulators, but all the simulators, while they are really good, they were lacking some of the properties that we need in order to simulate household activities. Either they are not fully interactive, or they are only allowing to move objects, but not other physical processes, or the actions are not very realistic. So that's why we have developed our own simulator based on NVIDIA's Omniverse simulation environment that we call iGibson. And what we have added in iGibson is physical processes that are necessary for many of these household activities, like thermal effects, transition machines, that is what we call to these special forward dynamics models, like blending things. We have lights and reflections of different kinds. We have fluid simulation, deformable simulation, and transparency. All of these properties or all of these features are necessary to simulate realistically many household activities. The simulator also provides very realistic interactions of the agents with objects. So here you see on the left, the typical rigid body physics that is available in almost any simulator, but in the case of iGibson with Omniverse, is very realistic in terms of friction. But we also enable interaction with soft materials and also with fluids, which is, as you can imagine, soft materials and fluids are a very big part of many of the tasks that we are interested in. All right, so I told you a little bit about the benchmark itself, about the scenes, the objects, and the simulator that supports it. So how much of a challenge is that for current embodied AI solutions, current robotic solutions? So what we did was to pick 3 of the 1,000 tasks, simplify them, and apply state-of-the-art algorithms to try to solve them and see how well they perform. So we pick 3 tasks: store decorations, collect trash, and clean the table on a very large restaurant where the agent has to navigate and interact with a flexible material. So the solutions that we evaluate 3 baseline solutions based on SAC and PPO, soft actor critic, and proximal policy optimization, which are RL policy learning algorithms that we embedded in different setups. For SAC, we do what is called visuo-motor control. At each time step, the policy receives a new observation from the onboard cameras of the robot, and it has to execute a robot, a joint command for each of the joints of the robot. And this happens at the normal frequency of the camera, which is 10 frames per second. For PPO, we did a different setup where we created a set of action primitives: pick, place, push, toggle, navigate, dip, and wipe. And PPO has to decide, based on the image, which one of these action primitives has to be applied and to what object. And then we have implementation of these action primitives, which is made based on a motion generator, a motion planner that decides on what trajectory to execute. The motion planner has some privileged information about the geometry of the work, and a trajectory executor, a trajectory controller that executes this trajectory. So what this does is to reduce, let's say, the length of the MDP, of the Markov decision process, because each action executes over several steps. And we have a third version of that, a third version of our setup, which is, again, the same setup with action primitives, but now we are going to keep register some history of what are the previous actions that the agent has taken. And this is additional information that we use for the policy. That way, we want to see if knowing its previous actions, having some memory, is beneficial for the robot. So in a very, very quick summary, I think most of you are probably familiar with reinforcement learning, but if not, in a nutshell, reinforcement learning is this general problem formalism where an agent performs actions in an environment and receives observations and rewards. And in RL, we assume that the model can be, the problem can be modeled as a partial observable Markov decision process that is represented by this tuple here. And the goal is to find a policy, a close to optimal policy, or even optimal policy, that tell us what action to take on each step in order to maximize the expected future cumulative reward. So this is, in a nutshell, reinforcement learning, and this is what we have been testing for behavior activities, and these are the results. Here you see each row is one of the baselines, and each column is one of the activities that we are evaluating: store decoration, collect trash, or clean up the table. And we see that for visuo-motor control with SAC, the policy performs very poorly, basically doesn't achieve any success. So our takeaway from this is that the activities in behavior are too long horizon for visuo-motor control. There is not enough signal from the sparse reward of achieving the task in order to find the right sequence of actions to perform these tasks. Then we evaluated PPO with action primitives, and we observed some partial success on the activities. What we obtained from this tell us that with the action primitives, what we effectively do is to reduce the horizon of the task, making it easier for the policy to find some successful strategies. And finally, adding memory actually brings improvement all over the activities, but especially for activities that have much more partial observability, where remembering what you have done before is very helpful to understand what should be the next activity, which is the case of the cleaning table, where the agent has to navigate from one side to another, and if it does not remember what was done before, it may repeat the same actions again and again. So these are the results in simulation, but our ultimate goal has been always to create solutions that we can bring into the real world. So in a second set of experiments, we went ahead and tried to measure the gap between our simulator in behavior 1K, which is of iGibson, and the real world. For that, we created a digital twin. First, we created a mock-up apartment in the basement of the university building, and then we created a digital twin of this mock-up apartment. And to do that, we scanned the mock-up apartment and replace all the objects by interactive models of the objects that were available. So here you see a video of the real and the simulated versions of the mock-up apartment, and you see that we try to match as much as possible all the models. They are IKEA furniture because IKEA furniture provides I mean, there are available models for almost all the furniture that you can find in IKEA, and you can see that there is a good match between both. So what did we learn with our real simulation to real experiments? So here you see the execution of a trained policy in simulation directly executed on the real robot. And what we learned is that thanks to our very realistic simulator, zero shots into real transfers partially to the real world. So what I mean with partially is that we obtain some partial success on some phases of this simplified task. This is a very simplistic version of cleaning after a wild party where there is only 2 glasses and two bottles to clean. We obtain partial success, meaning that some of these objects are cleaned up, but we never get full success on the entire task. Not all the objects are cleaned up. There is always one error or another appearing. And that tells us that actually zero shot sim to real is very difficult. So here you see some of the most representative errors. The first one is what we call policy error. The policy makes the wrong decision based on the image. In that case was to navigate to another location where it should have picked one of the objects that were in front. The second error is grasping error, which indicates that visuo-motor control, controlling the motion with the cameras, is actually very difficult. That also happens when the robot has to place objects. It's not executing the motion in an accurate way. And the last type of error that we have observed are navigation errors, because there are some obstacles on the floor, some carpets, the robot bounces and suddenly doesn't know exactly where it is, so it stops. So a little bit more in detail, what are the sources in error between sim and real can be observed here. First, and the first thing that to remark is that in simulation, we obtain 40% success on full execution of the task. So 40% of the time, the entire task can be achieved. But when we go with this policy to the real world, that drops to 0. There are no trials where the entire task is executed correctly. Only parts of the task are executed correctly. So then we ask ourselves, is this always because the policy is bad? And we design an interface where humans can tell what should be done next. That is what we call our Oracle human policy. And even with that, we only achieve 22% success, meaning that there are some other sources of error beyond the policy error. So analyzing semantically the sources of error, we see that in simulation, most of the errors comes from the policy taking the wrong decision. In real world with the policy, many of the errors comes from the policy, but actually the control of the motion for grasping, from placing, creates a big problem. And when the human is taking the decisions, there are no policy errors, but again, the dominating source of error is the execution of the right actions. So the main challenges here are long horizon planning, creating policies that actually can reason about what should be the next step, and sensory motor control of the actions, policies that accurately execute the motion that is requested by the agent based on onboard sensors. All right, okay, so this is the end of this first part of the presentation where I was talking about behavior, which is a benchmark of 1,000 household activities that aligns well to what humans want robots to do for them. Behavior is realistic, ecological, diverse, and complex. And I presented the results of evaluated state-of-the-art robot learning solutions. And we observed that they suffer because of the long horizon of the activities in behavior and the difficult visual-motor control tasks. And finally, I also presented some of the first sim-to-real experiments, zero-shot, that indicate that actually zero-shot transfer is very difficult. And it's going to need some additional help in order to bring the solutions from simulation to the real world. So I'm going to make a small pause here in case there are some questions about behavior, and then I will go into the second part. All right, okay, there are no questions. then I will move on. Okay, so these initial experiments with behavior are kind of like mixed. There are some successes, but a lot to do next. So what can we try next? So let me give you a glimpse of then the one of the projects where we are trying to improve results in behavior by basically doing better video prediction. Why video prediction? Well, as a reminder, this is the main results that we observe by trying to solve some of the tasks in behavior. Agents fail to plan the right sequence of actions for long horizon activities, and they fail to control the motion based on onboard sensors. For example, images. So this is what we focus in a recent project that we have submitted to ICRA, where we want to improve visuo-motor control, so the way the robot controls its own motion, using a better video prediction algorithm. So why that? How is the connection between video prediction and visuo-motor control? So the connection comes through what is called visual model predictive control. The idea of visual model predictive control is to query possible visual features from a video prediction algorithm and then compare, based on these possible features, where would I end up? And given a goal also in visual domain, I can compare my end of my possible visual future to where I want to be and take the trace, the set of actions that gives me a visual future that gets closer to my goal. Then I will execute these actions, and I will repeat again in an iterative loop where I basically predict possible futures, condition on possible actions of the agent, pick the future that is the one that brings me closer to my goal, and execute these actions. So clearly, what visual MPC depends on is a good visual prediction, a video prediction method that can be conditioned on actions. So how do we get that? If one observes the most recent successes in deep learning, they follow the same structure. They use a large amount of unlabeled web-scale data through self-supervised procedure that extracts the information that is in this data and encodes this information into some form of foundation model, for example, some transformer architecture. And then this general trained model or foundation model can be fine-tuned to generalize zero or few shot to several downstream tasks. This has been very successful in domains, for example, in language, which was the kind of like the original domain for this, but it has been also successfully imported into image, into computer vision, both based on the idea of using for training a masking paradigm, where you mask some parts of the large amount of data and you train you train your model to reconstruct the missing information. And that way, the model is self-supervised, trained on this large amount of data. The problem is that no one has been able to bring similar powerful ideas in a successful way to video prediction in a way that scales and that is fast enough for robotics. So that's kind of like the landscape that we encountered when we started to think on how to do better video prediction. In video prediction, the most successful approaches are Fitbit and Video GPT. Fitbit is a simple CNN-based architecture that provides fast inference and scales well in memory requirements, which is one of the main issues with video prediction. However, the architecture is custom-made for the type of data and is not adaptable to the training procedure of foundation models, this masking version that can make use of a lot of self-supervised label annotation. So a second state-of-the-art method is Video GPT, which is scalable and domain agnostic. and is based on autoregression, the idea that you query the model generates part of the information that has been masked, and then you query it again with this new information to regenerate all the missing information. The problem of video GPT and in general of regression methods is that the model scales quadratically in the memory with the size of features because of the way the transformer architecture is designed, and also is very slow because of the autoregressive method, which makes it not suited for robotic applications, for robot control. So our goal is to combine the best of these two works in a new domain agnostic method with low memory requirements and fast inference for robotics. So we took inspiration from models like video MAE, a state-of-the-art method for video recognition. What video MAE does is to train masking tokens randomly over space and over time, and learns to regenerate them, similar to what BERT and GPT-3 have been doing for language. So this procedure leverages a lot of videos out there in a self-supervised manner and achieves state-of-the-art results in activity recognition. So can we apply the same masking idea to video prediction and create a video prediction algorithm? Well, not really, because of the discrepancy that we would create between training and test time. Because if we train with masking some parts of the information, but providing part of the information about the future frames, this is not going to be available during test time, where in test time we only have one frame and we want to predict all the frames into the future. So if we train with this paradigm, purely with this paradigm, the performance is very poor. We need to adapt it. So to overcome these issues from existing video prediction methods, we proposed MaskVid, which is a mask video transformer method that has a two-stage training procedure. First, what we do is to learn an encoding of the visual data that discretizes images into tokens based on a discrete variational autoencoder and VQ-GAN. Then we pre-train a bidirectional transformer with window-restricted attention via masked visual modeling, meaning that we keep all tokens from the first frame, but mask many of the tokens, most of the tokens of the future frames, and train the transformer to regenerate them. In order to regenerate them, the transformer uses the information from all the tokens available through windows that span space and time dimensions. So in the same frame, what information is provided by other tokens, and along the time dimension, what information is provided by tokens in other frames. There are two important design decisions that make MaskVid different, that lead to the performance that we obtain. The first one is the use of this factorized attention in both space and time, with multiple blocks of window attention over frames and intra-frames. And this is important because it allows us to scale up, even obtain higher resolution predictions than other methods without a huge amount of memory consumption or amount of number of parameters, basically. And the second important decision was to use a high and variable masking ratio during training, meaning that during training, we ask our model to predict most of the tokens into the future with a variable amount of tokens provided, but this amount of tokens provided is very low. Basically, we try to provide as few information to our training process, to MaskVid during training process as possible in order to anneal towards the test setup, which is only providing the current frame and predict all the frames into the future. So that's actually what we're going to do during inference. During inference, remember that the only thing that we have is the first frame. So we are going to provide only the tokens of the first frame. And we are going to ask MASBIT to regenerate all possible frames into the future. We usually predict 16 frames, 8 frames, depending on the task. And then what we're going to do is we're going to keep only the most confident of these tokens based on a mask scheduling function that is going to tell us how many tokens to keep and how many to reject. So here you see the form of one of the scheduling functions that we use is a convex scheduling function. That means that at the beginning we reject most of the tokens. We keep only a few ones that are very, very certain, that MASBIT is very certain about these tokens to be correct. And then we iterate and repeat the prediction with these new tokens, regenerate the entire frames, keep more tokens again and again until we find the number of, end the number of iterations in our procedure. So an important difference to autoregressive methods, autoregressive methods predict each token based on the previous token, and then and again and again and again, meaning that it's very, very time consuming because it predicts one token at a time. Here we have also an iterative method, but it's not per token dimension. It predicts many tokens at the same time. In fact, all the tokens at the same time. So that's a big difference that makes the performance of our algorithm much faster and suited for robotics. So what we did was to compare MASBIT to several state-of-the-art prediction methods in multiple data sets, including the Kitty dataset that you are probably very familiar with, and the Bear dataset, which is a robotics dataset. And the results of MASBIT are indicated here in sub-rectangles, different versions of MASBIT, of our algorithm, that obtains superior or very comparable performance that is indicated by a lower FVD score, Frechet video distance. And at the same time, what MASBIT obtains is that good performance with a lower number of parameters that are necessary for the baselines. Basically, other methods require a larger model, which is also larger to train, more costly. We obtain better performance with lower number of parameters. Additionally, MASBIT, apart from less parameters, is the only model that can provide higher resolution predictions, 256 times 256, and is also the one that has the most flexible conditioning because of the transformer architecture that we use. We can condition only in the first frame and last frame, giving a goal. We can condition on intermediate frames, on actions, which is very important for model vision model predictive control, or even in language. Yeah, is there a question?
Yeah, a small question. Can you please go back to this comparison charts? Yeah, have you tried to compare with video MAE? Because I cannot see the comparison with. Yeah, I can see this fit width, mask width, but do not have a comparison with video MAE.
Yes, we didn't compare to video MAE because video MAE was not for video prediction. It was consuming entire videos for activity recognition. So the only thing that we got from video MAE was the training idea of masking in video domain. So these are the state-of-the-art algorithms for video prediction: Fitbit, GHVAE, SVG, and we have in the paper several others comparisons, especially depending on the data set. So in that we have difference.
But cannot we just use like how to say in the same way when we have for images, when we have mask out some sort of sub-image and then just trying to, as in birth, for example, to reconstruct this somehow, and the same to use the same for video, for example, to mask out the last frame, the predicted frame, for example, and then use it as Yes, as on BERT, for example, to predict these tokens for the last frame.
Yes, it could, but because the training is not, so that's one of the things that we did, especially in MassBit. We try to simulate or anneal the training process as much as possible to the test setup, which is you're only going to have one frame. In other methods, they don't do that because their test setup is not video prediction. So they assume they are going to have more information, which is video MAE case. They are not training for video prediction. They assume they're going to have many tokens available. They just do like in, let's say, in GPT-3, you don't mask most of the sentences, you just mask some of the words. So that is the similar idea here. That's why in our model we have done it differently. One of the design decisions was to have variable masking that is very high, so that basically here you see we start with masking almost everything. So this is the percentage of the prediction that is rejected in the first iterations. So you see that at the beginning, we basically reject everything. It's close to 1 in terms of the rejection fraction. And then we keep a few tokens, just the most confident ones, and we repeat again and again. And then we keep more and more. So that is different to generic masking in videos.
I see. So probably, if I understand this correctly, so the difference here in this like setting. So here we have only the first frame, and we need to predict like multiples, and
Yes.
not just we have like 5 frames, and we need to predict the 6th one.
Yes, exactly. So that's why the training process has to be adapted to that and brought closer to the test setup, which is just 1 frame and predict everything into the future.
Okay. Yeah. Thank you.
I think there is another question.
Yes. Hi, Roberto.
Hi.
I'm Brian. I'm curious, what would be the difference between masking in the latent space compared to masking in the input space?
Yeah, that's a good question. So it's actually a good question. I don't know. We didn't try to do it in the image space directly. So here we're trying to basically leverage the success of discretizing the code base of the image feature representation that is provided by methods like BQGAN. So they have shown that they are very good on compressing the information in an image because of this discretization of the information. So we wanted to work with this discretized feature space. That is our main reason for this 2-level training procedure, where we first discretize into tokens, and then we work with the tokens in the transformer architecture. So if you mask directly in images, that would be a good question. How would we adapt it? So then your input would be basically masked, and then the result of BQGAN would be basically affected by this masking. I'm not sure. At the end, what you want is to mask the input to your transformer. So that would change the architecture, because that would mean, are you not passing the features that you're masking to the transformer, but actually the images? That would make it a bit different of an architecture. But it's a good question. I don't know if that would be possible. I will have to think more about how to adapt the architecture to that.
Yeah, thanks. Because I was thinking, if you mask it at the beginning, you're losing those information at the beginning. But if you mask in the latent space, I don't know about the details of the architecture, but like you probably still have almost all the information from the input, even though you mask some tokens. The other tokens might share the full image information.
Yeah, so your question is if there is some information kind of like bleeding because what you're masking are the tokens in the latent space, not the kind of like geometric information of certain patch on the image. That is true. The question is, do you need to mask the geometric information in the image? Is that the right process to train the model at the end? or it doesn't matter if it's well semantically segmented information that you're masking or not. Does it make sense, my question? I don't know if that is the right thing that we want to achieve, or if it's fine that there is shared information in the latent space and we mask the latent codes.
Yeah, I guess that this is probably a question that we cannot find out the answer right now.
Exactly. It would be empirically, it would be interesting to explore it. But right now, I don't know what would be the result. I cannot kind of like think what would be best. But yeah, this is what we followed, and the results that we obtain are based on masking on the feature space. Yeah.
Gotcha. Thank you.
All right. So yeah, let me show you some qualitative results on the Kitty dataset. So here, I mean, I think this group is probably very familiar with Kitty, but it's a dataset of driving cars with cameras, and this is pretty difficult for video prediction methods because basically the entire image changes, especially when the car rotates. So even in those conditions, we get very good predictions, very, very plausible, realistic predictions that you can see here, for example, in the top right. Of course, the prediction is wrong. When you provide the first frame and you hallucinate the future, you don't know what can appear, but it's actually, I would say, very plausible visual future. Let me explain what you see here. What you see several columns of ground truth videos and mass bit predictions. For the mass bit prediction, only the first frame that you see in ground truth is provided to mass bit, and mass bit will generate the rest of the frames into the future. So what we see is that the results are pretty good, plausible, and kind of like good quality. So how does it do in robot data? So we tested in robot data. For example, here you see an example where, again, you see ground truth on the left and our prediction on the right. Only the first frame of ground truth is provided to massbit to do the predictions. And in general, what we observe is that massbit provides accurate predictions of the arm motion and also the wires and the background. Important here is that we are also providing the actions of the robot. With Kitty, there are no actions, or there are actions, but we don't know them. But here we are providing what are the actions in terms of what is the motion of the robot in order to do the predictions that you see. And I think there is a question. So yeah, happy to answer it.
Hello, I was curious, like for robotics tasks, like maybe some certain information in the image is more important than other, like let's say background or static.
Yeah.
So like for the utilization purpose, like what is your thoughts on that?
That's a very, very good question. So here's where I have two hats, and my computer vision hat says, well, we are working here in video prediction. We don't know our kind of like interfaces. We want to predict a video as accurately as possible, but my robotics hat says, what you said is exactly right. Why would I care equally about everything in my image when there is some parts, there is some information that is really critical and some other information that is actually not that important? There are some additional questions that would have to be solved, like how does the agent actually know, or how does the predicting algorithm knows what is actually task relevant information and what not? But that could be also something that may be learned. So I like your idea, and that's something that I'm exploring, an attention-driven prediction. Basically, focus your computational efforts on predicting what really matters and not what doesn't matter. But in this case, we're tackling as a full computer vision problem. We want to predict as good as possible. And the FBD, the distance that we use, it's a distance that is basically for the entire prediction. There is no information about what tasks is going to be, if there is a robot or not or anything. It's just about the quality of the prediction compared to ground truth at the image level. But you're completely right, and I agree with you. For robotics, this doesn't make sense completely. Why predicting all the pixels with equal kind of like importance?
Got it. Thanks.
All right. Yeah. So for robot data, we observe good, accurate predictions of robot motion, also the motion of the object that is being interacted, which is actually important even from a robotics perspective. And what we see is some kind of like lack of temporal coherence in the predictions of the background. Like, for example, there are some things that are not being interacted and change their shape in the background, things like that, that are kind of like a lack of understanding of this temporal coherence. Some additional results on robot data, you see here left for the pairs of, for the 3 columns, the left video is ground truth, must be video prediction, and then there are several examples here. So overall, we were very happy with the results. So then the question is, can we use it for model predictive control? So what we did first was evaluate how fast our algorithm is. We compared to the autoregressive methods that are being kind of like the state of the art right now, and we obtained a 3-digit speed up thanks to our iterative solution that is not predicting 1 token at a time. So that's fast enough for video MPC, visual MPC. So what we did was to embed our mass bit solution into a visual MPC solution that basically uses mass bit condition on actions to create traces. And we tested it in the setup that you see on the right, where the robot has to move objects to different locations, rearrange them, pick them, and place them somewhere else. And we obtained 60% success on these tasks on tabletop manipulation. Here you see a very simple example of how it looks like. The initial observation is on the left, in the middle, the goal observation, and here you see the execution of a visual path to put the object towards the goal. So this is the end of this second part, where I discuss how to improve interactive capabilities of our robot by creating more powerful video prediction methods. I presented MassBit, which is a new transformer-based video prediction solution that obtains better and faster predictions than autoregressive methods, and that can be used for robot control. As next steps, what we are doing is exploring how to extend MassBit to better predictions for grasping and placing operations. And I want to thank my collaborators here, Agrim, Stefan, Junsi, Yajun, and Fei-Fei. All right, so I'm coming to the end of my presentation. So I presented first behavior, which is a benchmark aligned to what humans want robots to do for them. And I also presented one of the directions that I'm following in my research to improve the performance of robot agents in tasks like the ones included in behavior by, for example, better video prediction capabilities. I want to show you, I didn't have time, but I want to show you another path that we are exploring to improve the performance of robots in behavior-like tasks, in the tasks that humans want them to do, which is to scale up domain randomization. We have a very realistic simulator, and we have the capabilities of exploring and creating diversity in simulation. So here you see the result of doing that, let's say brute force. Here we have trained in many kitchens to clean them up, to clean the cupboards and the drawers. And here the robot is tasked with the task of cleaning drawers and cupboards for 2 complete unseen kitchens, completely new in the real world. And we obtained 50% success after scaling up domain randomization. So this is really good, but at the same time, it's really bad because it took a lot of computational effort just for this very simple task and a lot of real-world training data. So what we are exploring is how to make use of domain randomization in a more tailored manner so that we can scale it up in order to obtain generalization in the dimensions that are necessary. So this is just flashing you with some fresh results that are being under review. And with this, I come to an end to my presentation. My idea is to continue exploring how to bring robots to do what humans actually want them to do in their homes. I want to thank you for your attention and your questions. And of course, if you have additional questions, I'm happy to answer them now.
Thank you for your talk, Professor Roberto. Let us, yes, virtually applaud you. And guys, yes, if you have any additional questions, please go on the line.
Yeah.
I have a question about specialized ICs, which are intended to be used for AI. And I just shared with in-call messages one of the development, which is coming to the market. Can you comment what applications you believe would be covered with ICs of this class?
Let me see. So this is about computation ICs that are adapted for
AI. So they have lower power, low cost, and allow something which traditionally would take significantly more embedded compute power to be executed.
Yeah, I think definitely. I mean, computation is one of the bottlenecks right now, and that's why we were looking at video prediction methods that are cheaper, say, to train and to execute, because they have a lower number of parameters. But it's true that in 10, 15 years, it may not be a big problem. But there's still a more fundamental question in terms of what is actually the structure of the solution if we would have infinite resources. And it's still unclear. So, of course, we have moved. The typical thing that everyone says is now you have in your phone the computation that was necessary to bring the man to the moon. But it's not like because we would have more computation, we know how to address problems like interacting and planning in the real world. Yes, we would alleviate some of the issues. Like, for example, you could train faster, you could hallucinate faster different futures, so do kind of like predictions into the future, more predictions into the future. But this is still unclear what should be the underlying structure to solve these problems. So I still think that while computation will bring a lot, and we have seen that there has been a revolution for deep learning, there is still the other side, which is how do we make use of this computation?
Thank you. Although I would like to highlight here that these are actually not, chips are not targeting high-end performance. So they are not competing with GPUs from NVIDIA or similar products. These are specifically mid to high-end edge chips. So it means that there are tasks out there in the real world which don't require enormous power, but these are definitely targeting embedding. So they are not so power hungry, they require less infrastructure to be used. So can you comment on tasks of where this can be embedded by providing useful real-world application, even though it's not the highest performance computational devices?
So that's where, sorry, can you repeat the question? So what tasks could we embed a chip in order to do exactly what?
Okay, so initially you were talking about then
improving
AI,
performance.
Yeah, AI being used in a real world. So you have some robots which are actually moving not just DALL-E pictures which come into the screen. So it's a real-world interaction. And once you deal with real-world interaction, you obviously start to concern about power consumption, about cost of the solution. And these are fairly new chips, which are targeting not the highest performance, but AI functions for something which I don't quite understand what is the niche. And if you have a vision, what niche of a robot can be using such inexpensive but not very high performance AI engines.
So if I understand what these chips do is probably optimized for deep neural networks, but I would have to look at more detail of what you have sent, because I don't know this Kendrick AI, but I can imagine it's mostly for high computing power, teraflops. Yeah, so what many of the chips are focusing on is to be able to perform faster inference for models, for deep neural network models. And that's the type of new chips that are embedded in, for example, Google phones that are adapted to run deep neural networks. And they kind of like, the architecture is optimized for that, because many of the solutions for vision, for computer vision, are basically just a feed-forward neural network at the end. So if you can reduce consumption of how to pass a feed-forward process into a neural network and accelerate speed for that specific model, not any general kind of like a computer model, but just for deep neural networks models, then yeah, that's a plus. So if that is what these specialized ICs do, I think it's just in terms of the demand of a better embodiment for these type of algorithms. So it's just improving performance for those algorithms that are the most successful solutions right now.
All right, thanks.
Welcome.
Any other questions? I think probably no yet. So thanks one more time, Professor Roberto. Yes, it was really inspiring. Let's like hope that in the nearest future we will have like robotics that really can help us in doing like all low-level things.
Yeah.
Like laundry, cleaning, cooking, etc. Currently, it seems like we can provide like poems and music and anything, but not cleaning and cooking. Yeah.
Yeah, that's right. At least that's one of my goals too.
Okay. Yeah. Thank you. Thank you. It was nice.
Thank you for the invitation. Thank you so much. Bye.
Bye.
Bye-bye.